I designed a custom watch movement, and today we're going to build it. Not only that, we're going to build it from raw brass and steel stock in the same garage I share with my kids' toys and yard tools. I have a couple years of experience servicing watches, and I've made enough individual components that I finally feel ready to maybe attempt such a project. Even so, my expectations are pretty low, to be honest. And without $1 million CNC at my disposal, I generally follow the methods outlined in George Daniels' book, Watchmaking. But alright, let's get on with it. Makera was kind enough to send me their Carvera Air CNC for this project. It produced beautiful results, but for certain componentry and their relationships, a more traditional non-CNC approach ultimately proved to be a better choice. Whether using this CNC or any other milling machine for that matter, repeatability is really important. You need a reliable way to remove and reinstall the workpiece without losing its position, especially for round parts like the movement plates. So I made a custom fixture plate that mates with Carvera's mounting screws and locating pins. The plate itself is then marked and pre-drilled with additional mounting holes and locating pin positions that actually correspond to the watch movement design. So that allows me to return each part exactly where it was for later tasks. Once the raw brass stock is squared off, I sandwich two of them together and stick them to the fixture plate. Now I can mill some of the features, and as you can see, this is the dial-up orientation. I pre-drill the center pilot hole, which will eventually be bored to size on the lathe, and the holes for the screws and the bridge locating pins are drilled through as well. Alright, for this first watch, I set some realistic goals for myself. I want to make everything from raw materials, with the exception of the mainspring, the hairspring, and the synthetic ruby jewels. Those simply aren't practical for me to manufacture in my home shop. The movement will be a simple key-wound 3-hand design with a Swiss lever escapement running at 18,000 beats per hour. Real simple. As for performance, my goal is to really just make it run, I guess. I mean, hopefully for the full duration of the mainspring. And in terms of accuracy, yeah, that's just kind of a bonus here. If I can get it to keep time within a minute per day on this first attempt, I'll consider that a win. I'm using some rods to position one of the plates to the fixture plate, so the holes can be tapped all the way through into the fixture plate itself. Only 3 are necessary, and it's enough to hold it down so that I can create the holes for the dial feet. I saved this part for later since I didn't want these holes going through the bridge plate when the two were sandwiched together. The profiling is being done with a 1mm end mill, but I probably didn't need to leave the tabs. I guess I was just nervous of the corner pieces being flung about inside the machine. The Mainspring Barrel houses the main spring, which is the power source of the watch. The barrel's diameter, the tooth count, and tooth geometry are all intentionally designed. Concentricity is super important when making the train of wheels. This is the one thing we need to get as close to perfect as possible, and is most easily achieved on the watchmaker's lathe. The dimensions of the blanks are all derived using equations defined in the BS 978 cycloidal gear standard. This index plate allows me to cut a variety of wheels. For example, one ring has 78 holes, which I'll be using for this mainspring barrel. If the cutter isn't perfectly centered, the teeth will look like they're bent over and asymmetrical. So once I'm happy with it, I can lock the slide and then proceed with cutting all 78 teeth. The vertical slide is height adjustable, so I can actually get the depth of the cut just right. The blank now gets flipped so I can mill away the excess teeth, leaving about 1.5 millimeters worth. In this position, I would also turn a little shelf, if you will, into the inner wall where the lid will snap onto, as well as bring the barrel closer to its final depth. The rest of the barrel is then brought to depth, leaving the bearing boss a bit oversized in the center, which I'll later reduce when I'm test fitting the arbor. Making the lid from a disc was pretty straightforward, and once I got a snap fit, I turned it flush with the walls of the barrel. The mainspring I've chosen for this has a T-end at the tail of the outer coil, which locks into matching slots in both the barrel and the lid. This is a roughed out mainspring arbor. Like all the other steel components in this watch, I'm using 01 tool steel, which I was able to buy in its annealed state. To maximize concentricity of the finished part, I decided to try turning between female centers. So the arbor blank was made pretty long and both ends were turned to a male taper. I don't think this is quite 60 degrees, but it worked well enough, which let me reverse the part without losing concentricity. This little part has a surprisingly difficult job. It has to securely drive the inner coil of the mainspring while withstanding the forces of winding. At the same time, its pivots need to run freely in 4 separate bearings, 2 in the barrel itself and 2 in the movement plates. Finally, one end will be filed square to accept the winding key. The hook is simply a small steel rod that's to be press fit off-center in the hub of the arbor. All these steel components need to be hardened and then tempered. Prior to hardening, I like to coat the part in borax mixed with some denatured alcohol, which helps prevent oxidation and scale from forming during that process. It does create a bit of a mess, but a short soak in scalding hot water helps to break that all down. After hardening, it's super hard and brittle, so it's tempered to blue over a bed of hot brass flakes to add a greater toughness, and then it can be finished. Brass provides a slower, more even heat than direct flame. As planned earlier, the oversized bearing bosses are now face down until the arbor spins freely inside the barrel. I'm intentionally leaving the arbor over length for now in case I need to mount it between centers again for any final adjustments later on. The second, third, and fourth wheels are next. In watchmaking, the mainspring barrel is generally considered the first wheel of the train. I'm starting with a pinion, and again I'm using annealed 01 tool steel. I'm choosing not to turn between centers because I need the work held in the chuck so it can be indexed for the cutting of the leaves. I still form a taper at the end though, since I'll still need to use some kind of tailstock support when it comes time to cut the pinion leaves. I later realized this approach could introduce some concentricity errors every time the part was rechucked, so I changed my process for the remaining pinions, as you'll see later. The cutter centering is even more critical for pinions, as any error is magnified due to the size of the leaves relative to the diameter of the blank. The center wheel pinion has 12 leaves, and that's kind of a lot, but it does carry the full torque coming directly from the barrel. The small watchmaker's lathes, like the one I'm using, aren't the most ideal for this kind of work, with rigidity being the limiting factor. You can still make the most of the setup by locking down as much as possible and taking multiple light passes rather than trying to remove too much material at once. With the leaves cut, I can then finish the other minor features of the part, such as the pivots and the rivet section where the wheel will sit. A properly hardened part will allow a file just to glide over its surface without biting into it. Once it's tempered though, hardness is reduced, and then I can finish the pinion by polishing the leaves with diamond paste applied to pegwood, followed by burnishing and polishing using the jacket attachments on the lathe. Not every part of this movement demands micrometers of accuracy. The wheel crossouts are mostly cosmetic, so this was the perfect place to let the CNC save me a few hours of handwork, since the manual alternative would have been, laying them out and then cutting them with a piercing saw. The small pilot hole will be drilled and bored concentric to the axis of the lathe, which will also be true to the outer diameter of the blank once it's turned down to size as well. I'm using what's traditionally called a wax chuck, although I'm actually bonding the blank with super glue instead of shellac. I did this with the barrel as well, but decided to use a screw-in variety from now on, as I was concerned rechucking the piece of brass would bite me at some point. The wheel blank is super glued onto it and remains there through all of the lathe steps: drilling, boring, cutting of all 80 teeth, so all features are concentric. As you can imagine, choosing the tooth counts for the wheels and pinions is one of the biggest parts of designing the movement. Their ratios determine how quickly power moves through the train, ultimately setting the rotational speed of the hands for a given escapement frequency. Not only that, the wheels also have to physically fit within the movement, of course, and avoid interfering with one another. And to simplify the build, I tried to limit myself to just a few gear modules, so I wouldn't need a different cutter for every wheel. The CNC actually did a beautiful job machining the crossouts, but they still need to be finished by hand with needle files. A little polishing cleaned them up nicely, although I'll ultimately replace the polished finish with a radial grain. You're seeing a lesson learned implemented on the third wheel pinion. I changed two things. First, I left enough material protruding from the chuck to finish the blank in a single setup, and that eliminates another rechucking operation. And second, I switched to female centers because a center drill naturally produces an accurate 60-degree taper that mates perfectly with the male centers in my tailstock. To finish off the top and bottom faces of the leaves, I'm trying this fine grit grinding wheel mounted into the vertical slide rest. It works surprisingly well, although I'll eventually need a better method for bringing these faces to a true mirror polish. One of George Daniels' clever ideas was to let the parts determine the movement layout instead of relying entirely on calculations. Every wheel, pinion, and cutter introduces tiny manufacturing errors. So rather than assuming the theoretical center distance, for example, this depthing tool lets me find the point where the two gears actually mesh the best. That center distance is then transferred directly to the main plate. Multiple reference points are used to place the center relative to other plate features. The movement gradually lays itself out as each wheel is completed. It's an elegant process, and exactly how movements were developed before modern CNC machining made theoretical dimensions almost perfectly repeatable. The third wheel itself is produced in the same manner as the second wheel. Since the pivots of the wheel are small enough, I can use my jacket tool rather than the lathe accessory to burnish them. I like this as I feel I have better control with it being much smaller and bow driven. The pivot sizes of the train are about 1/4 millimeter in diameter, roughly the thickness of a few sheets of paper. By this point, I felt like I was finally settling into a rhythm. The one challenging part though is the skinny extended pivot that will extend through the dial side, which the sub-seconds hand will have to mount to. I couldn't bring this section down to size quite yet, or the arbor would become too flexible to withstand the cutting forces while forming the leaves. I'll save that step to the end. After hardening and tempering, I can now finalize the upper and lower pivots. I like doing this now rather than in the annealed state because the very thin steel is less likely to bend and roll over the graver as easily. Because I'm using carbide gravers, they hold their edge pretty well enough to cut the hardened steel without frequent sharpening. This is where the truing tool tells me whether all that work actually paid off. I'm checking that the wheel runs true and is concentric with the pivots. Onto the escape wheel, which is technically the fifth and final wheel of the train, and an integral piece in the escapement mechanism. The pinion is made in a similar fashion as the last ones, but I will say it turned out to be one of the hardest parts in the movement. At just 1.2 millimeters in pitch diameter, the arbor was only about half that. It needed enough stick out for cutter clearance, but every extra millimeter reduced rigidity. It took a couple of attempts to get this right, and next time I might make a custom support to sit directly beneath the pinion while cutting the leaves. As for the wheel, the most preferable way to cut a club tooth escape wheel in steel would be to use a series of custom-made cutters, which I didn't feel very confident about getting right. I used the CNC instead. And yeah, I put a lot of trust in the Carvera. And yeah, I know what I said earlier about avoiding the CNC for critical parts. Believe me, I thought about that too, but I was genuinely curious about how well it could machine something this delicate, and the teeth themselves were profiled using a 0.3mm end mill. By some miracle, no end mills were harmed in the making of this part. The wheel and the faces of the teeth were polished after hardening and tempering the steel, and I tempered it to a straw color. Any roughness here becomes friction inside the escapement, so it was really important I got this right. It looks surprisingly good, but whether it actually functions as an escape wheel is another question entirely. George Daniels often said that the main plate is truth and everything else follows from it. Every wheel center I've carefully scribed up to this point has to be transferred to the bridge side of the movement now. If I'm even slightly off, the pivots won't line up when the movement goes together. So those reference points only matter if the bridges can return to the exact same position every time they're removed. That's the job of these locating pins. The screws simply clamp everything together. Before going any further, I do need to describe the locations of the pallet fork and the balance. Unlike the wheel train, these locations can't be found with a depthing tool. Here I'm trusting the original CAD design. If reality ends up differing slightly from the CAD model, I still have some room to adjust. Like I can fine-tune the pallet stone depths relative to the escape wheel, or I can make small changes when creating the balance roller. Most important are the locations relative to the other features. So, naturally, nothing could possibly go wrong. All I have now is a tiny punch mark in the brass. Somehow that mark has to become the exact center of rotation in the lathe. With the work mounted in the faceplate, I scribe a reference arc and align it to a fixed point, in this case the tip of a turning tool, making adjustments with a little tappity tap tap, as Blondie hacks would say. Now the hole can be drilled through and then bored undersize. These will be reamed to final dimension later to fit either bushings or jewels. And in the same setup, I'm now pocketing the recesses where each of the components will sit comfortably between the plates. Now it's simply a matter of repeating the process for every remaining feature in the plate. With the upper plate mounted back onto the fixture plate, the CNC machine can now profile all the bridges for me. Since this isn't critical geometry, the CNC can do this pretty quickly and I don't really need to stress out about micrometers of accuracy. For the first time, I'm confirming the fitment of the bridges to the main plate, held by the friction of the locating pins. It would be great if we had screws, so let's make some. I'll need 7 in total. I have to thank Mike Bolton from My Retro Watches for helping me secure this really nice, complete version tap and die set from the UK. Well, it was complete. Hey, I mean, I mean, it took one or two sacrifices for me to get a good feel for these delicate little taps. Apparently taps are consumables? Anywho, the screw blank from the 01 tool steel is turned to size and threaded with the appropriate die from the set. The tailstock's only providing light pressure, but is mainly there to keep the die perpendicular to the screw. A thin slitting saw cuts the screw slot precisely on center. The screw is hardened, tempered, and polished. I still haven't decided whether to leave it polished or give it a nice heat blue finish. Now that every screw hole exists, the arc method makes it easy to bring each one directly beneath the spindle before machining the counterbore. For ease of work holding, I have the bridge mounted to the main plate for this. The pilot holes created by the CNC are now enlarged to prepare for being tapped. In hindsight, I probably should have had the CNC drilled into this size from the get-go. Here's another clever trick I borrowed from George Daniels. It's called a wobble stick, and when trying to align a hole to the center of the lathe axes, it helps magnify any errors so you can know how to correct the part in the faceplate. This is absolutely critical to get right, since this alignment will be used to create the corresponding pivot hole in the upper bridge plate. If it's wrong, the wheels in the train will not sit completely vertically in the watch and, as you can imagine, cause all sorts of issues. The pilot hole was already there for the second wheel pivot, so all I needed to do was enlarge the hole for the boring bar. For creating all the other pivot holes, the process is largely the same, except I center drill first before drilling and boring. Drill bits tend to wander, and a boring bar corrects that error and brings the hole back onto the true axis of rotation. Those little CNC tabs had annoyed me for long enough, so it's high time we finally turned it down to its final diameter. And for this, I'm using you guessed it, a wax chuck and super glue. The barrel bridge still needs the little details that support the winding mechanism. The locations for the click spring, the ratchet wheel, and the guard plate. Thankfully, this is another job perfectly suited for the CNC, and I'm excited to use my new bridge screws to secure it to the fixture plate. Similar to what we did earlier with the main plate, I now need to remove material from the underside of the bridges so they can mount over the wheels. Rather than guessing the bridge height, I use little brass stand-ins that match the finished wheel heights. The recesses in the bridges are adjusted as much as possible to allow the bridges to seat completely to the main plate. Since I'll later install friction jewels, I'll have additional flexibility in dialing that end shape with the ability to raise or lower the jewels in the holes. Oh This took some figuring out. I messed up the scribes in the main plate. They transferred correctly to the balance cock, but they no longer agreed with the CAD model, which meant the beautifully machined CNC profile was now completely in the wrong place. I had to spend some extra time in CAD shifting the design to match reality, machine a new balance cock, and then repeat all the same operations to get it back to this point. It's a good reminder that in watchmaking, every operation depends on the last one being right. Just when I thought the design work was behind me, I found one more problem. There simply isn't enough room around the lower center wheel bearing to fit a standard jewel. Instead of redesigning the plate, I'm going to adapt and make a brass bushing which doesn't require me to ream it out as wide. I left it intentionally oversized in length, which allows me to face it down as desired after it's pressed into the plate. The hole through the bushing is slightly undersized though, so that I can later use a smoothing broach to enlarge it just enough for a smooth fit of the arbor. The barrel can finally be tested. Its bearings are already complete, so there's nothing left to do here for now. But let's hold up a sec. Before pressing in any jewels, I couldn't resist cleaning up the dial side with a fine radial grain. Not sure which way I prefer it, but one day I'd love to learn perlage. I think that would really take these movements to another level. Alright, now I'm ready to press in some jewels. These are friction fit jewels, so the holes in the plate are reamed to just 0.01 millimeters smaller than the jewel itself. The hole within the jewel is between 0.01 to 0.02 millimeters larger than the arbor or pivot, so that the wheel can turn without any binding, but not too much freedom, which would cause the wheel to shake side to side and result in depthing issues. As I mentioned earlier, I have a little bit of flexibility when setting the height of the jewel in the hole, so I can tighten up any excessive end shake as needed, which lets the wheel spin freely without excessive vertical play. One final machining operation lowers this section of the bridge to match the shorter fourth and escape wheels. As a bonus, I think the stepped profile gives the movement a little more visual interest. With the bridges still mounted, it's a convenient time to bring their outside diameter to the proportions of a standard 18 size movement. I created a little pump center on my wax chuck to make it easier to mount the plate on center. Okay, now it's finally starting to look like a watch movement. Whether it actually behaves like one, that's another matter entirely. Up to this point, I've only been making individual parts. This is about the time they all have to work together, and I'm about to find out whether months of design and machining and layout actually amounted to a functioning wheel train. As I fit the jewels, I'm incrementally test fitting the wheels. I think some of the end shake is a little much, and so I can simply press in the jewels a little bit further until that vertical free play is barely noticeable. As far as the depthing goes, the barrel to center wheel is perfect. Third wheel, fourth wheel to escape wheel is buttery smooth. Everything was going great until the second wheel met the third wheel, and this is what I was afraid of. It feels like they're just a hair too close together and they're binding pretty badly. I can't even get it to turn over. Gosh, it would be great if I could just move the hole over just a bit. Actually, I can, so let's do it. To do it, I first need to erase my mistake, create a fresh canvas, and scribe a new set of lines. So I ream both the upper and lower third wheel holes to accept a 3mm plug, which is then faced flush. Sure enough, my suspicions were correct. You can tell the crossing point is just a bit further than before. After all that, it's nice to take a break from the high stakes work and spend some time on the winding mechanism. The Carvera makes quick work of the ratchet wheel guard plate, and it's another perfect CNC job. The geometry isn't especially demanding, and I can spend my time on the finishing instead. The rest of the pieces, like the click spring, the ratchet wheel blank, are all milled out of a sheet of 01 tool steel. I use a 0.3mm end mill to rough out the square hole in what will be the center of the ratchet wheel. I'll finish it by hand later with needle files. Alternatively, a custom square brooch could have been built for that purpose as well, although I actually ended up making a brooch for the roller jewel later on, which you'll see when I get to the balance. I'm using a 60-degree 7mm ratchet cutter to form the teeth on my ratchet wheel blank. You may have noticed I started marking the index plate with a Sharpie. That's because of one spectacular indexing mistake that completely ruined a wheel. I wasn't exactly thrilled. Since then, the Sharpie has become a permanent part of this process. Everything is hardened first, but the click and the click spring are tempered to a blue color for greater toughness and springiness. The ratchet wheel is tempered only to a straw color, so it retains more hardness and better resists wear from repeated winding. Some of you might remember this polishing tool I made in a video a couple years ago. It keeps the parts perfectly flat while I work through progressively finer lapping films toward a mirror finish. Oh, I just love making screws, and I need to make another batch for all of this new hardware. Special attention goes to the click screw because it's a shouldered screw. The shoulder acts as the click's pivot, allowing it to rotate freely while the threaded portion simply holds everything in place. Everything's fitting well enough now that I can feel comfortable trimming the excess length from that barrel arbor that I intentionally left oversized. Everything up to this point has been leading here. The pallet fork of a Swiss lever escapement is arguably the most difficult component in the entire movement to design, manufacture, and tune. Assuming I even got the design right, that's a lot of adjustability, a lot of variables, and a lot of opportunities for frustration. Thankfully, I'm starting with the easiest part of the assembly, which is the pallet cock. Like the other bridges of the watch, this one will contain a small bearing for the upper pivot of the fork arbor. But unlike the others, it's super low profile as the balance wheel directly above it will need to clear it. Normally I'd let the CNC establish these holes, but thanks to the same debacle from earlier that led me to redesign the balance cock, I'll need to drill these without the help of the Carvera. 4 holes in total, 2 counterbore holes for the screws, and 2 for the locating pins. And yeah, the lathe can also be a weird looking drill press. The upper ends of the locating pins are riveted and then filed flush with the surface. I made 2 screws and they still need to be finished. These have flat heads, so I have an opportunity here to finish them with my new screw head polishing tool. It came with an assortment of collets to support a variety of screw sizes. There are other video tutorials out there, so check that out if you want to learn more about these particular tools. But basically, the screw heads are polished through progressively finer diamond compounds until they take on a mirror finish. The results were better than I'd hoped. The Carvera handled the pallet fork surprisingly well, leaving me with just one major component to make by hand, the arbor. Keeping in mind I'll have some flexibility as well with the jewel positioning. For an arbor that's less than 1 millimeter in diameter, there was no easy way to finish these pivots on the jacket tool, as none of my normal lathe dogs would work. So shout out to Dave Moss, he's a watchmaker in Oregon, who sent me this unique set of micro dogs. It's a beautifully simple design, as they're really just little spring-loaded pieces. The arbor's in, the jewels are fitted, and the end shake feels just right. Next, I'll work on the pallet's sight holes and the banking pins. The banking pins will be threaded into the main plate, so next I'm turning and threading a matching brass rod. The pins themselves, which the pallet fork banks against, are eccentric relative to the body of the rod. One way to achieve this is to create a fixture to thread the rod into, slightly off its center. Then the fixture is held in the lathe and I can slowly turn down the rod until all that's left is the pin itself. A screw head slot is manually cut on the reverse side of the rod. Because the pins are eccentric, simply turning the banking pin using the slot later lets me make tiny adjustments to the pallet fork's travel. This will allow me to adjust the safe entry and exit of the roller jewel relative to the fork horn. Both banking pins are installed and positioned to some nominal starting point that will need to be adjusted later after the balance is made. The pallet entry and exit jewels, seen here preparing for liftoff into orbit should you sneeze near them, will need to be installed in the tiny fork slots and then cemented into place. I made myself a tiny bottle of shellac goo, which is simply just a couple of flakes mixed with denatured alcohol. I have my trusty alcohol lamp and I'm ready to party like it's 1896. I'm using a piece of scrap brass from the bridge profiling step to evenly and gradually heat the shellac until it fully melts, settles into place, and then cures while it cools back to room temperature. For the first time, I can actually test the escapement, so I do need to temporarily install the train to put it under load. Nothing's been officially cleaned or oiled yet except for that barrel. I figure all the other parts will be touched quite a bit while the build is still going on, so I won't bother with that till later. I just need to test the pallet interaction with the escape wheel and incrementally make any adjustments to the pallet stones as needed. If the interaction isn't quite right, I can reheat the fork and then nudge the stones in and out before the shellac sets again. heart's racing. And we have a working escapement! Oh man, oh okay, it ain't pretty, but I don't even care. You have no idea how good this feels, how relieved I am that we've made it this far. We're not out of the woods yet. If the balance is the heart of the watch, it's also one of the most demanding components to get right. As its name suggests, it has to be perfectly poised, properly weighted, and run perfectly flat and true. Its oscillation determines the rate of the watch, making it one of the most critical parts in the entire movement. The balance cock hardware seen here include the regulator pieces, which are used to fine-tune the timekeeping after assembly. That and all the other balance components were made from O1 Tools steel and finished like the other parts. Gosh, this is nice to look at. Alright, back to it. Still need to drill and tap a tiny hole in this plate for the hairspring stud screw. Barely larger than the size of a hair, this will be one of 2 brass regulator pins. The hairspring will breathe between these 2 regulator pins, and by changing the spring's effective length, they allow for finer adjustments of the watch's rate. I'm borrowing a design cue from the Swiss when it comes to the lower end zone setting. It's common on those watches to mill a recess into the dial side of the plate and then secure it with a single screw. The setting will ultimately have a friction cap jewel pressed into it. The balance staff runs on this cap jewel above and within a matching hole jewel in the plate below it. Similar to the plate, the balance cock has a special hole jewel for conical type pivots, and the setting above it has the solid cap jewel. The Carvera roughs out the balance wheel slightly oversized. This is intentional because I'll finish it on the lathe so that the rim runs perfectly concentric with the center hole where the staff will eventually be installed. The 4th axis of the Carvera comes in handy here for drilling perfectly spaced holes for the balance weights and the timing screws that will eventually be installed on the balance. Making a balance staff almost feels routine now, which is kind of funny to say, because not that long ago, simply replacing one with a new old stock staff felt like a major milestone in my watchmaking journey. Then, making my first balance staff from scratch felt impossible, until it wasn't. So it's kind of satisfying to look back and realize how much of those skills have grown. The upper and lower pivots of the balance staff have to run perfectly coaxial with each other. So my recommendation here is to complete the whole thing in one chucking setup, leaving the pivots oversized in diameter and length to finish in the jacket lathe. With one end stone removed, I can incrementally shorten the pivots to final length until the end shake is just right. Only then it's time to rivet the balance onto the staff and check it for trueness. The roller jewel is shaped like a semicircle, less than half a millimeter in size, and it needs to be installed in the roller table I'm making next. To accomplish this, I'm creating a tiny brooch that will allow me to form a perfectly shaped hole in the table to fit the jewel. After hardening and a light temper, the brooch is mounted in one of my staking set punches, which gives me much better control. The roller table was simply a disc made from 01 steel with a pilot hole drilled to accept the brooch. That slight deformation along the edge is inconsequential since I'm filing that part away anyway with a round profile needle file, and that's to form the crescent to clear the safety pin of the fork. After hardening, tempering, and polishing as per usual, the table is ready to accept the jewel, which is then cemented into place with shellac. There's a special tool I'm using designed specifically for roller tables. I have a dab of shellac sitting on the edge of it that I use for reference just to more easily see how warm the tool is. The roller is friction fit onto the lower section of the balance staff so it sits flush against the hub, and I'm doing this using a specially relieved stake that protects the roller jewel during installation. Though I don't have a hairspring on here yet, I can still observe the smooth interaction of the balance and the pallet fork and how that allows the passing of each escape wheel tooth, and the resulting impulse propels the balance to the other side. At this point I can make the safety pin of the pallet fork, and its only job is to make sure that if the watch receives a shock, the pallet fork always remains on the correct side of the impulse jewel. The hairspring is one of the few parts I didn't make myself. After trying a few candidates, I found one that only needed minor adjustments to work on this regulator. Its position on the balance isn't arbitrary. That orientation determines the resting position of the impulse jewel relative to the pallet fork, and that minimizes what's known as beat error. It's ticking. What an incredible feeling. Oh, it sounds so beautiful. And fast. But that's expected. The balance doesn't have any timing screws installed yet, so it's far too light for this hairspring. At this final stage of the project, I'm focused almost exclusively on the balance, so I'll put another round of hand finishing on the plates and pieces before running it through the cleaner for the very first time. I made up my mind and I will be heat bluing the plate screws as I feel it will offer a nicer contrast and variety compared to the polished steel appearance. In general, I use HP 1300 on the barrel, second and third wheel pivots, 9010 everywhere else, and Mobius 941 on the pallet stones. I still need to slow the balance down, and I'll do that in 2 stages. First, timing screws add mass to the rim, increasing the balance moment of inertia and slowing its oscillation. Then, a pair of meantime screws provide finer adjustment by changing how that mass is distributed around the wheel. I intentionally made the screws oversized, and as you'll hear, the balance is now much too slow. From there, it's simply a matter of carefully removing material until the rate comes into the range, while also bringing the balance into poise so there are no heavy spots. This will help with positional accuracy. Material is incrementally added by way of timing weights or removed to bring the balance into poise and to keep within the regulating distance of 18,000 beats per hour. When I'm happy with it, I can continue to monitor and tweak the performance with the help of the time grapher. And honestly, I'm thrilled with these numbers. No, it wouldn't pass railroad standards, but that never really was the goal. 7 months ago, this started as bars of brass and steel, a CAD model, and a lot of hope. There was lots of coffee consumed, and I made plenty of mistakes along the way. Some of them were frustrating enough that I really wondered whether I'd painted myself into a corner, but somehow it all came together into something that actually keeps time. I learned an incredible amount building this movement, and there is a huge list of lessons learned for the next time. I'd love to know what part of this project surprised you the most, so let me know down in the comments. I could probably sit here and watch this thing tick all day, but until next time, thanks for making watches with me today, and I'll see you in the next one.